we're gonna comb this tree from left to right. You see?
Yes, I see now.
We're gonna count the numbers from smallest to largest, like this.
Yes.
Right?
Mm-hmm.
So this is like I'm just gonna replace 3 with the smallest item in my larger side, in 3's larger side, and everything still works. All the rules still hold, and we can still do the scanning, and we're walking the numbers in order still. Okay, so last time we went into details about how to add a node to a tree. What is the big goal of this algorithm?
Adding the node to the tree.
Adding the node. So we said like we're gonna like this window. We're gonna move it down the tree, and we can only ski down one path. We can and when you find the place to insert yourself, you're gonna insert yourself, right? And that place is always under a leaf node. So a node that has room has null pointers either on its left child or its right child, so you can insert yourself there.
Yes.
Yep. So that's the algorithm. And did we write it down here? Yeah, we wrote it down here, more or less. We had some questions about specifics about how to know whether you need to insert yourself to the parent's left side or the right side.
Right.
And I think there are different ways to do it, and I kind of came up with a way on the fly, which will probably work. It may not necessarily be the most elegant way, but that doesn't really matter. That's just the details. But what I want to get at now is like, what was the big goal of this algorithm?
I think log in.
Yeah. Why is it log in?
Because we only have to. I feel like I'm going to butcher this explanation, but I'll try. We only have to, for each level we go down, it's only like one more operation.
Mm-hmm.
Like, I don't feel like that's a good explanation of why.
How many levels are there to the tree relative to n, which is the number of nodes in the entire tree? That's the key.
Yeah. And believe it or not, I actually have looked at this since we last talked because I know it was a hard subject or hard for me.
So like we have the entire tree that has all these nodes. I think there's 7 here.
7, yep.
And given a tree with 7 nodes, there are 3 levels, right?
Right.
So that's the key, the connection between the number of elements in the full tree. If I tell you there are this number of elements, n elements, how many levels tall is this tree? And that relationship is represented with log of n, log base 2 of n, more specifically.
Okay.
So yeah, because the other side, the other relationship is exponential. Like if I told you I had a tree that has 3 levels, then you know that the size, the number of nodes in the tree is 2 to the 3rd power, 2 to the 3rd.
Okay.
Well, -1, but
right,
that's not important.
For the root. But that one makes way more sense. I can wrap my head around that one. So I just really have to drive home that the log in is the inverse of that one.
Exactly. It's just the inverse of power, of taking a power. Yep.
Okay.
Yep. So that's why we get the log. Yep. So cool. I think this and updating is. I'm gonna skip over updating because that's not super interesting. It's just you just retrieve the node and then you update its. Oh, actually no, you can't just update a thing. Or not the key anyway. But when I say updating, I really mean like you're not updating the key, but maybe the data that's associated with the key.
But what about if if you're updating the data, not the is the key the thing that is compared? The key is like 9 versus 8 versus 10.
So imagine each node is not just a number, but it's like a customer. It has all kinds of customer data, but the number is just the customer ID.
Okay.
Yeah. Or instead of sorting by the ID, which might not be super useful, you might want to sort by the customer last name.
Okay.
Which gets us back to that phone book application, right?
Sure.
So yeah. So if I say
the piece we're not updating is our comparison value, whatever that may be.
Correct. Yeah.
Okay.
So if you need to change the key, that's a big deal. You will need to remove it and then add a new one back in, basically. But if you're just updating the phone number, which is not the key, then you're just retrieving the node and then changing a field inside. That's all you're doing.
Okay. I'm with you. That all makes sense.
Okay. So for that reason, I'll just skip the updating, but basically it's also a big O of log n.
Okay.
Because it's same as retrieval. So let's talk about deletion today, which is the most funky one of all of them. Okay. So maybe I'm running out of room over there, so just write delete. How do you delete a node from a tree? Well, if it were like, let's say you have 5, 3, 7, 2, 4. Oh, I'm doing everything in order. Okay. So it's something like this. If you need to delete a leaf node, obviously that's very easy. Yeah, yes. You did delete 6, just get rid of it. But if you needed to delete, what is the term for a non-leaf? Is it an internal node? It might be an internal node, is a non-leaf node. Okay. So if you need to delete an internal node, it's actually well, I don't want to say hard, but definitely harder than just getting rid of something. So let's try to think about, and I had to look it up to remind myself how to do it.
Okay.
So let's say I needed to remove 3 from this tree. How would we do this?
Okay. Well, you're going to have to handle all its children. I mean, I right off the bat, that's the first thing that comes to mind. It's like, if I remove 3, 2 and 4 in this instance are going to have to be reorganized appropriately within the rules of the binary tree.
Right.
So my instinct, and I'm guessing that this is not at all right, but I'm just going to say it anyway, is that we would remove everything under the node. Like we have to remove everything, every child 2. Like we have to remove them all. If we remove 3, 2, and 4 also must be removed and put back in. But there's got to be some other solution. But that's kind of my first thought.
Okay, just add them back.
Just add them back, yeah.
Okay, so then 2 would go here, and then 4 would go here afterwards.
But that's, I mean, depending on how big the tree is, how many children are under the removed node, that could be a lot.
Yeah,
So,
it could be a lot if you're removing the root, for example.
yeah.
Then
It would be a lot.
you're adding back all of the tree except
Right,
for that
you're-
one node, which
You're
would be
deleting your tree and starting it.
yeah, which would be the big O of that?
That would be big O of N.
Yeah,
You're
that'd be-
recreating the whole thing. Yeah.
yeah, exactly. So let's not do that.
Okay.
Okay. So, what else can we do? And I have to admit, I don't. This is non-intuitive for me, and I had to review it. But
Okay.
even now, I'm not so. I'm not so certain, and in a way, that's good because I think we should really understand why we should do this, and and let's say, so one idea. Okay, so maybe we'll try to come up with another strategy.
Okay.
And I kind of know in the back of my mind, I know what the correct answer is, but I'm gonna try to forget about that just for a moment.
Okay.
So, well, we could, well, okay, 3 used to be here, and 3's left child was 2, and its right child was 4, right?
Right.
And we need to stick 2 children under 5, right?
Yes.
So maybe we make one of them the left child of 5. Both of them are going to be smaller than 5, so either one should work. So maybe if I put 2 as the left child of 5, then I can put 4 as the right child of 2, and that seems to work for this case. Okay.
Yes. Yes.
But that can break down, and I'll show you why. That can break down because, well, let's not make another. I'm just gonna reuse this same tree.
Sure.
It can break down if I want to move this. If I want to remove 5, so I want a case where your immediate children are also internal nodes, right?
Okay.
Actually, I'm a little confused. Hold on.
Sure.
Do I want to? Hold on. No, I don't want to do 5 just yet. I want to add more children to these guys.
Okay.
Oh boy. This is gonna be 1. This is gonna be 2.5. Well, these things I have to make some room here. This is gonna be 3.5. This is gonna be 4.5. Okay. And I want to remove 3. So I'm gonna move 3 out. And then I have to either choose 4 or 2 to be the immediate descendant of 5. and let's say I choose 4, and
Okay.
then if I choose 4, then 2 can be the left descendant of 4.
Yep, that makes sense.
But 4 already had 2 existing children. So where are they gonna go? Well, you could like 4 can't have 3 children, so one of them is gonna have to go. Let's say is 3.5 has to go. Where is 3.5 going to go? I don't know. Maybe under 3.5 is gonna have to go this way because it's less than 4, right? So will we have to add 3.5 back in the subtree?
Why can't it go to the right of 4.5? Right child of 4.5?
Because it's less than 4, so it has to be in the left side of 4. It used to be on the left side of 4.
Oh, okay.
But I drew the lines in this way to make room. But yeah.
Okay. I'm missing something, which I probably just need a review. I thought that, okay, when we're putting a new number in, like let's say we were just about to add 3.5 for the first time ever. 3.5 is the next number. It would be to the right of 5, then to the right of 4. But then we already have a number that's then it would be to the left of 2.
You go to, or it should have been left, and then
Yeah,
right.
I'm sorry. I meant left.
Yeah.
I'm getting backwards.
Yeah.
And
then
then it would end up to the left of 2.5. Right?
Right.
That's where it would end up. Okay. Okay, I see. So we can't just stick it to the left of 4.5. Okay. Sorry.
Yeah.
I just had to talk that out. Thanks.
Yep. So there might be a way to do it like this, but it'll potentially have to rearrange all the way down, right? But I think if you did it this way, this will also be big O of log n though, because right? Because we're just moving down the whole tree. Like the worst case, we're going down to the bottom of the tree.
Right.
I think.
It's like inserting something new. It would be right. Almost.
Yeah. Because it's like inserting because there's like an extra child that we need to make room for, and then we're inserting it in this subtree.
Right.
Yeah, that's below it. I think that could work. Okay, maybe we've invented a new way to do it, but the textbook way is not this.
Okay.
So, but I kind of want to. Let me think. So I think this method should work. I don't know why they don't do it this way, but the textbook way is. Let me see. I'm gonna go back to what it was first.
Sure.
Was it like this?
Yeah, I think so. But then you had 2 more.
Oh yeah, I had
Another
2.
level. Yeah.
Oh wait, I can undo, right? Yes, I can undo. Yes. Okay. Nice job. All right. So, so the textbook way to actually do the delete, so we want to delete 3, is actually, I think you take the smallest item from, so you remove, let's first remove 3.
Okay.
And then I think you make, I think what you do is you replace 3 with the smallest item in the bigger side,
Okay.
which in this case is 3.5. Does that make sense?
Yeah, that does. And then everything else can stay where it is.
Exactly. So there's less movement, and it also makes sense why that works. Like it's the smallest. You could also do the other way around, which would be you could do the biggest item in the smaller side also, right? You could replace
Okay.
yourself with 2.5, and that would also work.
Yeah, it would. I'm still trying to wrap my mind around why it works, but I'm slow thinker.
Yeah, I think the reason why it works is if go back to the binary search algorithm with the array.
Right.
If you look, well, this, I'm gonna fix this graph a little bit, make more room here. So that they are actually lined up and sorted correctly. Okay. So if you just comb the tree from left to right, then you get an increasing order, right?
If you do what? If you
If you scan this tree from left to the right,
scan it. Okay.
scan like there was a line that is moving from left to right, uh, like this. There's a line, and we're gonna comb this tree from left to right. You see?
Yes, I see. I see now. Yep.
We're gonna count the numbers from smallest to largest, like this.
Yes.
Right?
Mhm.
So the reason why just replacing 3 with the smallest item in its bigger side is because that number is right next to 3 in this ordering.
Yes. Okay. Okay.
And
I see that.
and it would be the same if we took the biggest item from its smaller side. It would be the same.
There'd be either number that would be immediately to the right or left of that number if they were all lined up in a row.
Yeah, if it were a sorted array, then yeah, 2.5 would be right before 3, and 3.5 would be right after 3.
Yes. Okay. That's
And
really cool.
and there is why. So with we talked about with arrays, it's really annoying to remove stuff because you have to shift everybody after it over by 1, and that is a big O of n operation.
Right.
So that's really annoying. So we're doing that with trees now. And the interesting thing with trees is because the tree is like arranged in this kind of dynamic fashion where, we're not all packed into bins, but we're like we know where everything is just based on our relationship with each other. You can dynamically change those relationships. So yeah. So this is like I'm just gonna replace 3 with the smallest item in my larger side, in 3's larger side, and everything still works. All the rules still hold, and we can still do the scanning, and we're and we're walking the numbers in order still.
That's really cool.
Yeah.
Yeah, that's just really neat.
Yeah, so then the question is, well, okay, before we say what the big O is. I really like that scanning thing.
Yeah, that's a good visual. It's really cool. I'm still amazed by it. I didn't see that before. I didn't see that one coming.
Yeah, cool. Yeah, we discovered it together. So yeah, so this one is gonna become null at the end of everything. So let's try to write this algorithm out first. So how do you delete a number? Uh, first you first you do the retrieval, basically, like
Yes.
use retrieve algo to find node you want to delete. No, this is really big now. Because I zoomed in by a lot, I think this is fine. So that was step one. And step two, basically replace self with smallest node in your bigger side, which would be the right side.
Right.
And then well, you're gonna I guess maybe this is too broad, this statement, so maybe there's two steps to that.
I was
So
just thinking that, but I thought maybe you were trying to do a higher level.
yeah, I think it's helpful to like describe things in a higher level, but let's also go lower level.
Okay.
Like if a high level statement is very clear to humans and unambiguous, then that's really helpful. But in order to replace yourself with the smallest node, first you have to traverse. Well, actually, how to find smallest node?
Yeah.
In right child. Now, interestingly, the algorithm for finding the smallest node in a tree, which I'm calling, I mean, the right child is just a tree. Okay.
Right. Yeah.
It doesn't matter that it's a subtree. A subtree is still a tree, and it satisfies all the rules of a binary search tree, just like your larger tree. So I can say, I need a algorithm to find the smallest node in a tree. So maybe we'll come back to that. What is algo to find smallest node in BST, which is short for binary search tree?
Okay.
And then after you've found that, remove that smallest node, and then we have to come back up the tree somehow. And then place 3 node with the smallest found node. So that's the algorithm. Let's go over this item because it's somewhat interesting. How to find smallest node in a BST. So you can temporarily forget about this deleting a node from the tree problem and just think about if I gave you any binary search tree, how do you find the smallest node in it?
Okay. So because I know I am going for the smallest, I know I'm going to be dealing with the left hand
Yeah.
side.
Yeah.
So I can immediately cut it in half and be like, I need to search down the left side.
Right.
And then I want to keep going left and left and left until I hit a null value. And I know that the value before the null value is the smallest.
Exactly. Yeah. Yeah. So you don't have to do this if statement that we would have to do when we're searching for something specific. We're just always going left.
Yeah.
Exactly. That's the difference. And what is the, well, let me write it down first. So basically, while let's say current node is equal to root node,
Okay.
I'll just say root. While current node is not null, and current node is equal to left node, right? Left child. And then oh, hold on. Then we're gonna, after this loop, we're gonna lose what the previous one was.
Right. So we need to be storing it every time.
Like maybe I have prev node is equal to or another way is while current node's left is not null. So while
I like that. That's
left
better.
node is not null. When I say left node, I mean of current node. But this is pseudocode, so I don't have to be precise. Well, left node is not null, then current node is equal to left child, and at the end, you just say return the current node. There's probably an edge case that I missed, which is if the current node is already null, then that's a problem. But whatever. This is pseudocode. I don't have to run it. So I think if you actually program it, you'll find those edge cases, and then you have to deal with them. So something like this. What is the big O of this algorithm?
You're going to have to go all the way down the levels. It's log n.
Yep. Yep. It's again, it's log n. So okay. So now that we figured out how to find the smallest node in a binary search tree, and we know it's worth it's big O, it's performance runtime. We come back here, and we know this is big O of log n, this substep of this deletion algorithm. So after we find it, we're gonna remove that smallest node. Well, we're removing it from the bottom of a tree, right?
Right.
So that's the easiest case. It's just gonna
case, yeah.
unlink it. That's gonna be a big O of 1.
Yep.
And then come back up the tree.
It seems like we should have stored our starting point somewhere. So we can just go right back to
we don't actually have to climb back up the tree. It can
Okay.
be, it can be just like at when we were at over here, right? Back then it was 3 that was here, so it was like this. When we were here, we can just call into a routine that would go down the tree, find 3.5, and then also delete it from that tree all in one go. And then when that function call is done, we're back up here. So
Okay.
That doesn't actually take any extra work.
Okay.
So yeah. So and that's not really a step even. So maybe we don't even count that. But yeah. And then we're gonna replace the 3 with the node that was found. So we are, I mean, we could even reuse the node. We just override the value of the node.
Yeah.
So
Yeah.
so that's just bigger of 1. And then this retrieval to find it, the thing you want to delete is a big O of log n again.
Yep.
So yeah, so the whole thing is big O of log n because the worst 2 cases are big O of log n. So that's how you delete stuff from a binary tree.
Yeah, that's pretty neat. I'm fascinated by the concept. It's so simple, and yeah, I feel like I would never have come up with that.
Yeah,
It's very
it's
intelligent design.
it's very, yeah, once you see it, you're like, yeah, it's very obvious. But if you had to come up with that yourself, it might take a while.
Yeah.
I would say there's a lot of problems that are like that though, where like finding the simple and elegant solution is actually very difficult. Like you have to try a lot of different solutions and then see that a lot of them are bad before
Yeah.
you find the one. It's more of a search. Like you're just looking in all the different corners all the for something good, and then when you find it, it's like finding gold. And then I that's how I see problem solving.
Yeah.
Which is why I think it helps, and I think that like there's a lot of work problems that I've approached that way, um, and it helps to take things slow, I think, and not be in a rush to implement the first idea that comes to mind.
Yeah. That's the hard thing about balance in a environment where you're producing something for someone, is that this like you have to the productivity aspect of commercial work balancing with like getting the best ideas, and that sometimes take time and a whole bunch of iterations. It's like
Yes,
it seems like an eternal like balance issue for those
it
of us
is.
that are working in it. So
Yeah,
interesting thought.
I think it's yeah, it's you have to always balance that. I agree. Well, even if you're not, hmm, even if you're not working in a company, you're working on your personal projects. I think that balance is still an issue.
Mm,
Um, even though you can, yeah, you can if you want to take more time, you can. But there's also a limit there because if things just keep dragging on and on, then you feel like you're not doing anything productive.
yeah.
Um, okay. Let me think. Okay, so maybe we'll just talk about um, how to keep a tree balanced.
Yes, I've been waiting for this. I've been thinking about this and thinking about this, and I don't have good answers, but I have questions.
Okay, so so there's several so there's a thing called self-balancing trees, first of all.
Okay.
So if we Google for self-balancing trees, this bar on top is in my way. how can I get rid of it? Oh, it went away. Okay. Self-balancing binary tree. There's many different variants of self-balancing trees, and this is the list of of them.
Wow.
It's like a, well, it used to be a very and in some ways, like I think the weight balance tree. No, the weight balance tree is still pretty old. Okay. It's in the 70s. So it was a big area of research in computer science.
Okay.
Probably not today anymore, but but they figured out many different ways. I would say probably the most famous one is the red-black tree, and maybe AVL tree are the two most famous ones. But then the weight balance tree made a resurgence a little bit in recent years because some, I want to say Haskell, like some functional programming languages decided to use weight balance trees
Okay.
instead of the red-black trees. Red-black trees, I believe, is commonly used. I think this is the one used in the Java standard library. If you use a hash in Java, it uses this red-black tree. And then the standard library in Haskell uses a weight balanced tree. And then the AVL tree, I don't know which things actually use the AVL tree, but they all center around one idea, which is, so I'm not going to go into the specifics of the individual ones actually.
Okay.
Partially because I haven't studied them recently. I have studied weight balance tree and red-black tree, and I have implemented them myself, but they're complicated enough that if I don't study it just like the night before, I probably won't remember how to do them.
Fair. Very fair.
So that's how complicated they are. I'm the sessions I've been doing with you just off the cuff, the stuff that I like know well enough to present them, and this
Yeah.
is not one of them.
Fair. That's fair. You talked about the red-black tree a little bit in the video I watched on databases, and
Yes.
my head was spinning pretty quickly. I was like,
Oh,
okay, wait. I need to slow down. I need to go back. It was very complex.
Yeah. So but I'm gonna talk about the general ideas that all of them use, which
Okay.
is simply detecting when a tree is out of balance and then fixing, right?
Okay.
So the self-balanced trees all have they detect when a tree is out of balance and then fix it when it deems necessary. And that's in a nutshell. That's what they do. Now, before drilling into that, though, I do want to mention a devil's advocate argument, which says, if your self-balancing trees are not necessary if the stuff that's coming in is random.
Okay.
Like statistically, if you have a insertion into the tree that is random, then it'll be more or less balanced. And so maybe you don't really have to, and people have done experiments and tested this. And so some people claim that it's not necessary as long as your data coming in is random. But as we have shown, often it's very easy to write a program that inserts things into a tree that's not in a random way, right?
Yeah. It's like getting things to be truly random. Like it seems like random enough to solve this issue is more complex than you would think it would be. Is kind of my thought, my initial thought.
Yeah, it could be. Yeah. Like generating random numbers is another science that you could really dig deep into as well. So yeah, I agree with that sentiment. So how do you detect when a tree is out of balance? So that's the first question. And then the second question is, how do you fix it when it's necessary? And what does necessary mean? So, well, one way you could do it is just by, and this is the weight balance tree method, is on each node of the tree, they would add an extra field that tells them the number of nodes that are present in this subtree. So they would add an extra field. I'll put it in red. And so here there's 1, and here there's 1, here there's 2, and here there is, well, 1, 2, 3, 4, 5, 6. Here there's 6. I should have done the subtree first. So this is 1. Here is 2. No, this is wrong. This should be 3. Yeah. So your number is the number of your left child plus the number of your right child plus 1, right?
You're counting yourself. Okay.
Yeah, because you count yourself. So yeah. So in weight balance trees, which might be the one that's easier to explain, this is what they do. Oh no, again, this should be 3. Forget to add 1. So this should be 10 now, I think. 3 plus 6 plus 3 plus 1. 10.
Yep.
So by this way, you have this is like caching the count, because you could also just go through the entire tree and get the number. But this is caching the count in each node, so you can access them quickly. And the reason you want to access it quickly is because you want to be able to tell if things are out of balance. And in this case, well, 6 is greater than 3. So it is not balanced, right?
Right.
So, but how much out of balance do you deem it necessary to do something about it? That's a question, and that's a bit of I don't have a straightforward answer either. In weight balance tree, it's a parameter. It's like a factor. It's like a ratio that you multiply. That says if it's this, if the left side is this % bigger than the right side, then we should do something about it. Yeah.
Sure. It makes sense that it might be varying degrees of I don't know, weightedness that you care about for different things.
Yep.
Degrees of balance. Yeah.
So I think that's probably as much as I'm gonna say about that. And in red black tree, they have a very interesting method of figuring out sort of when a tree is out of balance and you need to do something about it. And then in the AVL tree, I think they keep the difference instead of keeping the absolute number of the count. AVL tree, they keep the difference between the left side and the right side.
I see.
And then they try to keep that difference within 1 or within 2, I believe. Like they can't be out of balance more than 2. But with the weight balance tree, there's a factor that So I'm just gonna hand wave over that. So that's how you detect if the tree is out of balance. How do you fix it when I deem it necessary? Let's talk about that.
Okay.
Are we at time? We're at
Yeah,
time.
we are at time. Maybe we pick
Okay.
up with that next time.
Yeah, I don't want to rush this actually. So let's talk about that next time.
Okay.
This is called tree rotation. Tree rotation. And we'll talk about this next time.